there is a way to make popping the back and adding before cheap. Right? Our problem was that although we had a way to get from a previous element to the next element, we had no way to get back. And what a doubly linked list says is, well, let's go ahead and add a way to get back. So we'll have 2 pointers, forward and back pointers. That's the bidirectional arrow we're showing here conceptually. And the way we would actually implement this is with a node that adds an extra pointer. So we'd have not only a next pointer, we'd have a previous pointer. So this shows, for example, that the 10 element has a next pointer that points to 4, but a previous pointer that points to 7. So at any node, we can either go forward or we can go backwards. So that means if we're trying to pop the back, that's going to work pretty well. What we're going to do is update the tail pointer to point to the previous element, because again, we could get there in order 1 operation, and then update its next pointer to be nil, and then finally remove the node. So that's order 1. So if we have a doubly linked list, it's slightly more complicated, our code, because we've got to make sure to manage both prev pointers as well as next pointers. So if we're pushing something in the back, we'll allocate a new node. If the tail is nil, which means it's empty, then we just have a single node whose prev and next pointers are both nil, and the head and tail both point to it. Otherwise, we need to update the tail's next pointer to this new node, right, because we're pushing at the end, and then go update the prev pointer of this new node to point to the old tail, and then finally update the tail to this new node. Okay. Popping the back, also pretty straightforward. We're going to again check to see whether this is first an empty list, in which case it's an error, a list with only 1 element, in which case it's simple. Otherwise, we're going to go ahead and update our tail to be the prev tail, and then update the next of that node to be nil. Adding after, fairly simple. Again, we just need to maintain the prev pointer. But adding before also now works, in the sense that we can allocate our node, our new node, and its prev pointer will be the prev pointer of the existing node we're adding before. Okay, so we splice it in that way, and then we'll update the next pointer of that previous node to point to our new node. And finally, just in case we were adding before the head, we need to update the head. So in a singly linked list, we saw the costs of things. The working with the front of the list was cheap. Working with the back of the list with no tail was all linear time. If we added a tail, it was easy to push something at the end, easy to retrieve something at the end, but hard to remove something at the end. By switching to a doubly linked list, removing from the end the popped back becomes now an order 1 operation, as does adding before, which used to be a linear time operation. One thing to point out as we contrast arrays versus linked lists. So in arrays, we have random access in the sense that it's constant time to access any element. That makes things like a binary search very simple, where we start searching in the middle and then tell if we have a sorted array, and then can decide which side of the array we're on and then go to one side or the other. For a linked list, that doesn't work. Finding the middle element is an expensive operation because you've got to start either at the head or the tail and work your way into the middle. So that's an order in operation to get any particular element. Big difference in between that and an array. However, linked lists are constant time to insert at or remove from the front. Unlike arrays, right? We saw with arrays, if you want to insert from the front or remove from the front, it's going to take you order n time because you may have to move a bunch of elements. If you have a tail and doubly linked, it's also constant time to work at the end of the list. So you can get, add, and remove from there. It's linear time to find an arbitrary element. The list elements are not contiguous as they are in an array. You have separately allocated locations of memory, and then there are pointers between them. And then with a doubly linked list, it's also constant time to insert between nodes or to remove a node.